Hello everyone. So today we are going to discuss about the first order second movement method, FOSM, which is a part of your fourth unit. The fourth unit we have FOSM. So let me start with first a brief recap of our failure function. So our failure function G that I have is a function of certain number of variables x1, x2, x3, xn, where xi's can be my, we have already discussed it might be material properties, material constants or material properties, okay, like your Young's modulus, Poisson's ratio, material properties, or they might be geometric properties. Geometric properties may include like the depth of the section, the moment of inertia, etc., all those quantities. So x's can be either material properties or they might be geometric properties. And so this is my failure equation. The failure equation depends on these quantities. So this is also known as the limit state equation. Limit state equation, or the limit state function. Okay, this So this is the limit state equation or the limit state function, which is a function of my variables x1, x2, x3, xn. Now we are already aware of our margin of safety function m equals r minus s. Okay, where r is the resistance and s is the action here. Okay, and m is the margin of safety. Margin of safety, the margin of safety function. Okay, I think I went out of view. So margin of safety function is equals to r minus s. S is my resistance and r is my resistance and s is my action. So this margin of safety function is the same as my limit state equation. So this m is equal to g x1 x2 xn, right? And we are already aware of what happens when this margin of these two variables in the margin of safety function change, or like how they can determine whether our structural element or the structure itself is safe or is not safe, is not reliable at all. So how do we do that? So if r is less than s, then definitely I'll have safety, then safe, right? And if r is or if s is greater than r, then failure is going to occur for sure. Failure. Then failure is going to occur if s is greater than r, and if r is greater than, the resistance is greater than my action, definitely I'm going to have safety. And if my action is greater than the resistance that my element can offer, then I'll have failure, right? So in that scenario, what do I have? If m, which is r minus s, if r minus s is greater than 0, which means r is greater than s, then I have safety, right? And we already have discussed a little bit of those before. And if it's less than 0, then it is failure, correct? So in other words, my g function my g function g x1 x2 xn, if this g is less than 0, I'll have failure, and if it is greater than 0, then it is safe, right? So if it is less than 0, I'll have my failure, and if it is greater than 0, then my structure is going to be in safe hands. Okay. So now how to determine the probability of failure? So that is the important thing, because if I can find out the probability of failure, I can find out the probability of safety or the reliability of the structure. So now suppose let me take two variables, a and b. I have two variables a and b. If a and b both are occurring at the same time, which means probability of a intersection b is equal to what? Probability of a multiplied by probability of b if they are independent. If a and b are independent. If a and b are independent, probability of a times probability of b, or if they are not independent, if there is a conditional thing in between them, then probability of a by b times probability of b. A by b means conditional probability of a given that b has already occurred times the probability of b. So if these are not independent, so dependent. If these are dependent quantities, I'll have this equation, and these are independent quantities. I'll just simply multiply probability of a multiply probability of b. Okay. So now I also have to find out the probabilities of all those variables that are involved here. So the probability of x1, any variable x1, is going to be what? If you have the probability distribution function of x1, so it's going to be the integration of the distribution function till whatever range you want it to be. And till that point, what is the probability if you have to find out? So probability of x1 would be integration of your probability distribution function, where this is your probability distribution function. Distribution function. Okay. So probability of failure, if I say probability of failure with respect to my x1 would be, I'll integrate this distribution function, but till what point? Till the point of failure, right? Till the point of failure means until unless g is less than 0. Till the point from minus infinity or whichever range your x is going to start. From that point till the point until unless g is less than 0, because if I see before, I have discussed here that if g is less than 0, when g is less than 0, I'll have failure. So till the point when g is less than 0, till that point, if I integrate it and find out the total probability, integrate my probability distribution function, find out the cumulative or the total probability, that is going to be the probability of failure dependent on my x1 quantity. So similarly, it will be dependent on all the quantities x2, x3, x4, x5, xn, and all those quantities are independent in nature. Therefore, the total probability of failure of the structure would be integration of all those fxi's, correct? Until unless g is less than 0. Why? Because you know that since x1, x2, x3 are independent, we have to multiply the probabilities, just like I have shown you here, that since these are independent, so P1, PA into PB, if A and B are independent. So similarly, since x1, x2, x3 and those material properties and all of them are independent of each other, like let's say the Young's modulus. The Young's modulus, which is not going to depend on the depth of the beam, right? It's going to depend on its own nature. It depends from material to material. Steel will have a different Young's modulus. Wood is going to have a different Young's modulus. So Young's modulus won't be dependent on the size, the length, or something like that. So these are all independent variables. So if I have to find out the total probability of failure, I have to multiply all those individual probabilities till what point? Till the point that g is less than 0. Okay. So what I can do is, depending on these ideas, I can actually give a graphical understanding of my failure, the failure function. So this g x1 x2 xn, I told you when it is less than 0, it is going to be failure, and if it is greater than 0, it's going to be safe. What happens when it is equal to 0? So this is something like a boundary line. If you are going beyond that, then you will have failure, and if you are within that range, you are within the safe shell, the safety of it. And if you are crossing this boundary, you are going to be on the failure side. So this boundary or the borderline that we have here is called the margin of safety. Just hold on one second. Yeah, function. Yeah. I'll just check once whether I'm using the right terminology or not. Is equal to 0. Yeah, this is the sorry, this is failure surface, I guess. This is failure surface. I use a wrong terminology, I'm sorry. Failure surface. Okay, this is a failure surface. The margin of safety was M. I'm so sorry that I messed up this thing. Okay, so this is the failure surface. This is where is going to be the border. You cross that, you are on the failure side, and if you are within that range, then you are on the safe side. So I'll just plot it and we'll get a graphical understanding of this, how this one functions. Okay, so this is I'll just take two variables, x1 and x2, because this is what is used in the book, even x1 and x2. So I'll have a surface like this. Okay, it's not necessary that it's going to be a parabola or some elliptical surface like that. It can be anything depending on the equation, on how these are dependent on the various variables. So I'll have a surface like this. This is assume that this is the surface. So this is my failure surface. Okay, so here this is the failure surface. Where my G is equal to 0. Correct. The failure surface when my G is equal to 0 and M is also equal to 0. The margin of safety is also equal to 0. Within this, anywhere inside this, I'm going to be safe. Okay, so this is where G is going to be greater than 0. So this is going to be the safe zone for me. Inside this is safety. G is greater than 0. This is going to be safe for me. If I go beyond this, this is where G is going to be less than 0, and this is going to give me my failure. So if I cross this failure surface, I'm going to have failure, and if I'm within this failure surface, I'm going to be on the safe side. So this is a graphical way of understanding how this failure function gives us an idea about, or how this failure might occur. So since we have margin of safety function G, now I have seen that this margin of safety function is actually dependent on R and S, where R and S can be again dependent on those quantities. R can be a function of, R can be some function, let's say f1 of x1 ... xn. Okay, this can be a function of that, and even S can be a function of f2, some other function of x1 ... xn. Okay, these can be functions of this. So if R and S are functions of x1, x2 and xn, then definitely M is also going to be a function of x1, x2 and xn. But basically what we have is M is a function of R and S. So now we have studied in the previous unit that the probability of failure in such a case is minus infinity to plus infinity. Fx of S into fr of x. If you go back to your notes, you will find out how we had derived this in the class, that fs of x and fr of x. So fs is my probability distribution function, of S, and fr was my cumulative distribution function, the cumulative probability of the cumulative distribution function, cumulative distribution of R. Okay, so this is going to be my probability of failure. This is going to be my probability of failure. So basically what we understood, how this failure surface, I can find out the equation, how I understand that when it's going to be failure and when it's going to be safe, within the nutshell, when it is inside the cocoon. So you have to understand it like this: when it's inside the cocoon, it's going to be safe, and when it goes outside the cocoon, there's going to be failure. Okay, and if you already know the distribution of R and S, so this is like when we have the failure surface or the failure function only described using my x1, x2, x3 the variables. If I have all the data of R and S, the resistance and S, how this R and S are, maybe they may be how the normally distributed, they may be log normally distributed, I know the mu of R, I know the mu of S, I have all the statistical data. The probability distribution function of R and S is known to me, so probability of failure is easy for me to find out from minus infinity to plus infinity. The probability distribution of S, the probability distribution of the action, and the cumulative distribution of R.